Now, just a strong introduction to myself, and I am a platform engineer at ZenML. So ZenML is the open source framework. I started off as a student intern last year in December, and now this year I've transitioned to full-time role there. I enjoy coding, sports, music, and like every other tech bro, I also enjoy hacking in the nature. So that's something I never turned down. This is my Twitter, and all right, so the title of the talk is FOMO on the coolest new MLOps tool. Here's a solution that can let you switch anytime. So ultimately, what the theme of the talk would be is that since MLOps is a very emerging field, you have so many new tools coming up. There are multiple startups which focus on the broad range of problems to solve. But you as a data scientist, how do you fix on any single tool to use in your workflow? Right? You can have MLflow for experiment tracking. You can also have weights and biases. And there are multiple other options available. So there is no, how hard it is to actually find out the right tool for your workflow. And the only way to do it is through experimentation, right? And how do you make your life simpler with experimentation? You can't go ahead and learn every tool you want and then build a POC on top of that, then evaluate if it's right or not, right? So it needs to have a very standard way, very easy way of doing all this stuff. So that's what we'll be discussing today. So having said that, let's move on to first some kind of context setting. So machine learning in the industry is not just about training models. So a lot of times you have this perception that, okay, machine learning means, okay, I have to train this kind of model using this architecture, this hyperparameters, all that stuff. But machine learning in the industry is much more than just training. Even the previous speakers, they mentioned that the ML part is just a very small box, but then you have this entire ecosystem on top of that. You have maintenance, you have monitoring, then data monitoring, all of that is also part of ML in the industry. It's much different than what we see on the notebooks, on the Jupyter notebooks that we have. So like this tweet by Chip Yuan and Elon Musk also agrees to that. So that's just a bit of a context. Now, ML in production, this is what we think it looks like. So there are multiple stages. You have data collection, which is the first stage, where you go ahead and collect data. Then you do some kind of training in the model and all that. And then finally deployment. So it feels like a very one-way kind of process in our minds. That, okay, I'll collect data first, I'll do some training, and then I'll produce in the whatever production I have. But the thing is, the reality is, it's always like a back and forth process. So you have some kind of data, you're training a model on that data, but sometime a new data comes in, like a better data comes in, then you have to again go back to collection, then again processing the data, and then again training the model. And even in production, you have to keep monitoring the kind of data your model is getting. So if there's new data which is coming in, you also have to go back and do the training again. So it's not a straightforward process. It always happens in multiple directions. So what I'm getting to using this diagram is that you need some kind of structure in your workflow that is reproducible, that allows you to easily design such solutions and have some kind of CI/CD pipelines where you can just trigger, some kind of workflow. For example, you can set if new data comes in, I automatically want to do this trigger happening. So there needs to be some kind of way to define pipelines in machine learning as well. So yeah, that's a short introduction. And again, I'll just reiterate the theme of this thing. So we'll be talking about a framework that will allow you to define your pipelines in such a way that you can always switch tools as easy as you want. And then you also even change the cloud itself. So not specifically on Azure, you can even switch to GCP or AWS, and the code will be agnostic of all of that. So the code is tool agnostic and as well as cloud agnostic. So that's the way forward. Let's get back to the problem at hand. So as I said, this is a very complex MLOps landscape. When you're out there venturing into the world and then you're finding out what tool to use, you come across this whole bunch of different tools in front of you. And it's pretty hard to figure out what tool to use for your production. But an easy way of understanding these tools is by first understanding what the ML lifecycle looks like. So when you first figure out, okay, these are the different stages in MLOps, then you can easily put each of these other tools in one of the other brackets, right? So for example, I can have, say, let's go back. Maybe I'll select MLflow, right? So it's very tough to actually figure out what tools there are, but if I can put them in different buckets, then I can study them individually. Like I can maybe take about MLflow is used for experiment tracking. So this is one part of it. And then I can easily figure out what options I have in that particular field. So just to go over this once, so usually it starts with data. So you have multiple concerns even in data. You have versioning. You have to take care of versioning of data because that's also super important. Whenever new data comes in, you have to change the version of it. So DVC is a tool which really helps you with data versioning. There's experiment tracking. Experiment tracking is really crucial because it happens all across the ML lifecycle. Like even when you're training a model, you have to track your hyperparameters. Like when I change some of the value of the hyperparameter, what accuracy did I get? Like we also saw the MLflow portal in the previous talk. So they were showing you parameters, metrics, all that stuff as well. So that comes under experiment tracking. So this is part of the data. Then there's the model which has training, all that stuff. There's automated validations, which is also validating if your data is right, if the rules are set in the right way. This deployment which checks that your model is ready in production, it is healthy, and the data which is coming to it is also very healthy. So all of this form a part of the ML lifecycle. And once you understand these different boxes, then what you can do is you can figure out that every tool is part of one of these components. So here I have 4 different components. There are multiple other, but I'm just using 4 as an example. So you have something like an orchestrator. You have something like experiment tracker, deployer, artifact store. There can be more. There can be data validators and all these things. So it really helps to think of these in terms of these boxes. So I can now take the tools which I had earlier and put them into each of these different buckets. So for example, Kubeflow, Azure machine learning, Airflow. You might have heard of Airflow, it's pretty popular. So all of these form a part of orchestration. Right? So orchestration is something where your actual code runs, where your pipeline is defined, where that pipeline is executed. That forms part of the orchestration, like the compute which you have. Right? So Azure ML has a lot of compute in the background. Kubeflow can be deployed on your cluster, your Kubernetes cluster, and then you can run it there. So that forms a part of orchestration. Then there's experiment tracking, right? That's another concern itself. So you have tools like MLflow, which is really popular. We saw that earlier. There's weights and biases, there's Neptune. There are many other startups coming up. Like you can just search for experiment tracking MLOps, you'll find 5 more startups there. So that's the idea behind it. And then you can have artifact stores. Artifact stores are just essentially the place where you store all your artifacts, like your models, your data, all those things. So that can be an S3 bucket, that can be Google Cloud Storage, Microsoft Azure, whatever possibilities are there. As well as the model deployer stuff is also really, really exciting. There's Bento-ML, which is really nice. There's Selden Core, Kserve. So again, host of options in every stack component. And these are just 4 stack components. You can have, as I said, more stack components going forward. And all of these stack components solve one of these problems. Like so experiment tracking is solved by the experiment tracker. There's orchestration which deals with the model training and all that stuff. There's model deployer. So each of these components covers some or the other part of the ML workflow. And they work together to actually help build your pipeline. Now, what we are going to do in our demo going forward, we'll be taking all these components and putting them together in a pipeline in a way which is composable. You can swap each of these elements out. For example, orchestrator, I'm using Kubeflow. I'll swap it for, say, Airflow with a single command. So that's what we're going to do. We're designing it in a very composable way where each of these components can have multiple implementations, like abstraction kind of design. All right, so now coming back to the problem, we have this thing called, now so since the tools are here, like the problem that we face, like as I said already, it's selecting the right tool for your job. So it mostly involves experimenting with the tool. Like you have to first get to know what the tool is, what the API looks like, how do you configure that with your workflow, what authentications you have to set, what secrets there are, how to deploy that thing. Just take the example of MLflow. Like, have you used MLflow before? Like, how many of you have MLflow before? None of you? Okay, so like, yeah, they have used it. So using MLflow, you have to deploy it somewhere, first of all, and then you have to set up some kind of authentication layer on top of it. Like maybe, say, using an Kubernetes ingress or something like that, so that you can protect your MLflow server, the tracking server. I'm not talking about anything else, but just a MLflow tracking server. So that needs to be your job. You have to deploy it on your cluster, then expose it through some kind of URL, and then safeguard it through some basic authentication. All that stuff needs to be done. Right? That is a part of using MLflow. And then you get to use it, then you get to know the API, then you integrate that into your notebook. So that is the entire process for a single tool. And now, for example, you figure out that MLflow is not the right choice for you. You want to maybe try weights and biases as well. So what do you do now? You sign up for weights and biases subscription, you create an account there. Again, the same process happens. You learn what the API is. Like that's a huge process, and a lot of time gets consumed while you're figuring out the tool. And this time also blocks other kinds of development in your machine learning lifecycle. For example, if you are not fixed on what tool to use for experiment tracking, you can't go forward and create the rest of the pipeline, right? You have to, because rest of the pipeline will also change if you change the tool. So it all hinges on what tool you use. So that's why it's kind of a blocker in which, not in a good way. So it stalls the entire development process, right? So that's some of the problems that I'm talking about right now. This is just a slide from the documentation which I have. This is ML documentation. It helps you just check between different tools. So like we have these pages for every stack component. And you can have, say, there's a comparison between deep checks, evidently, great expectations. All of these are data validators. Data validators, again, a stack component in itself. And you can see there are multiple features that are listed here. So this in itself, the documentation, helps you select what tool to use. But even the documentation itself is not sufficient, right? You cannot rely just on this documentation to figure out the right one. You also have to experiment yourself, as I said before. You have to try each of these out, and then maybe figure out what the right is for you. Yeah, this is already something I covered. Like I just skipped past that previous slide. So again, the first problem is high cost of experimentation, as I said. You have to learn the tool. Then you have to develop all these things, and it also blocks the rest of the development effort. The other problem that is there is a FOMO. So that's the major highlight of the talk. So a lot of people feel that, okay, when a new tool comes in, it might have better features, more shinier features than the previous one. There's always something which is better than the last one. So how do you cope with that? Because there are stories around say for example, Nokia didn't take up Android, they failed around. So a lot of people have that conception that, okay, I am with MLflow right now, it's a legacy software with me. Some new tool comes up like weights and biases, and now I'm not going to switch because my entire workflow is tied to MLflow, right? So they're not trying to switch, but ultimately there's something in the background which says that, okay, maybe some other competitor might use weights and biases and have an edge on me, right? So you always have that thing in the background that there might be a fear of missing out on new technologies, right? So that's also one of the other problems on top of the experimentation cost and all the other stuff. So how do you design a solution that helps you lower the cost of experimentation while also allowing you to switch between different tools so that you can cope with your FOMO, right? So if you think about it, one solution for that could be having something like an abstraction. So you define your pipeline only in terms of abstractions. So you don't define in terms of MLflow, don't define in terms of weights and biases, define in terms of experiment trackers. So I'll say that my pipeline, the first step should be data collection. Data collection will be done by a feature store. I won't talk about Feast or some other feature store. I'll just say it's a feature store. And then the feature store goes to the next step, which is training step, which is an orchestrator. So all of the pipeline which I'm defining right now will be done in terms of some abstractions. And when these abstractions are defined, then you can change the implementations going forward. So I can segregate the pipeline code, the code which defines the machine learning application, and the stack. The stack here means the tools and the other things that you use for your pipelines. Like where do you run your pipeline, what tools are going to use, that forms a part of the stack. So essentially, if you think about it, if I separate the pipeline code from the stack, then essentially I've achieved my goal, right? Because now I can easily keep the code the same way it is. I can even fast track development of the pipeline. I don't have to worry about the tool selection. I can defer the decision of selecting the tools to a later point in time. But right now I can just define my pipeline right away. I'll say, okay, this is how my pipeline looks like. These are the steps. These are the combinations. And I can think about the tooling system later. I can just define the stack whenever I want in the future. If a new tool comes in, I'll just change the stack to a newer stack, and then the same pipeline is going to run on the new tool system. So that's how you can have a composable abstraction kind of solution for it. And this is the framework I'm talking about, ZenML. So ZenML is an open source framework that allows you to have this kind of separation between these two tools. And since it's open source, you can deploy it on your own infrastructure. You can have develop your own integration. So if a new tool comes in, you can develop your own integration for it. So it's pretty simple to do that. They have these helpers, and the abstractions are really, really handy. So you don't have to worry about a lot of code yourself. And most of the time, it's open source, so a lot of community contributions are there. So the majority of the tools that you already know, like MLflow and all these things, even Seldon, Kserve, you name it, most of these tools have an integration with ZenML. So you don't have to worry about writing the code yourself. And a lot of people are designing things on Azure ML and other tools as well. Even for SageMaker or Vertex AI, you have integrations for it. So you can run from your ZenML pipeline. The same pipeline can run on SageMaker, and the same can also run on Vertex AI or Azure ML. So how cool is that? You don't have to worry about the cloud itself. You can just skip past that thing. All right, so enough for the talking. I'll just show you some code here, first of all. How this happens, okay, I'll go back. So this is how you define it. So you have a Python interface, first of all. So you define in terms of Python functions. So each of the steps are different Python function, and that is done through a decorator, like add step. So this step defines a particular step, and then you define a pipeline using a combination of these steps. So you tell ZenML what the different steps are. You give that code to ZenML. Now ZenML is packaged that into some kind of an image, and it runs it in a pipeline on any stack you want. That is how the entire things looks like. And all the tools that you need, they form a part of the stack, right? So this pipeline has different kind of tools, as I said already. So it has some experiment tracker, it has a model deployer. So all of these are separate from the pipeline. You take this separate away from the pipeline into a ZenML stack. So ZenML stack is nothing but just a configuration. It's not something of itself. It's just a configuration file that has all the information about all the different kinds of tooling or different kinds of, say, stack components that you're going to use with your pipelines, right? So secret managers, experiment trackers, step operators, all of these terms are ZenML, not ZenML specific, but you can find them on the documentation page. There are a lot of details about what each of these are, and there's also a handy comparison chart that I showed you earlier, how you can compare between different tools as well. Yeah, so this is the essence of it. Now I'll just show you a very fun comparison between not using ZenML and not using ZenML. So let's say I'll take an use case of switching between artifact stores, right? So whenever you do model training, you have an artifact store. which essentially stores your model artifacts and other kinds of files that are related to your training, right? So let's say I am working first of all with S3. I have an S3 bucket where I store everything regarding my model training. But now let's say I want to move to Azure. That can be a plausible use case. Like maybe you moved your cloud, you got credits on Azure, which you want to use. So if you want to switch between, say, S3 to Azure, what is your first step? Like, how do you imagine it in the first instance? I'll give you a second to think about it. Let's say you have this pipeline that you have defined, right? You have some code, which is a helper code. Maybe let's say it uploads your files to S3 and all that stuff. And then you use this helper somewhere in your pipeline. Like, for example, after training, all that stuff, you have these things. So I have this example here. If you look at it, so let's say I have an importer step. So it's a like general way how you do it in your notebooks. So you have an importer Python function. It takes in some URL where you'll get your data from, and then converts it to a data frame, like pandas data frame, simple as that. So what you do, you define all your code here, and at the end, you upload it to your S3. So this S3 is a class that I have defined myself. Like I have to write my S3 class, whatever class there is. I'll use the Boto3 library or some other library, and then I'll upload that to my S3 bucket, right? And then this is the same for the training step and all that stuff here. So when I change the implementation, like when I change from S3 to Azure, what I'll do is I'll have to create a new class, maybe an Azure class or something like that. And then each of my functions has to change as well. So ultimately, my pipeline code has to get modified a bit whenever I change a tool. Like it's a very simple transition. Like even in cases which are far more complex, you'll have even more changes. Right now, it's just like S3 to Azure, but maybe in the future, if you have some more complex changes, you might have to change more than single line of code as well. So, okay, this is the first thing. What I do is I just change this particular function call in my pipeline code, and I'm done with it. But the other thing is I also have to change the class. So this is the class definition. So the first time I'm having a S3 class and I define I use the Boto3 library. I just use my URL, all that stuff here, I do this thing. When I'm moving to Azure, I'll have to create a new class. I'll have to figure out what tools to use. I can't use Boto anymore, but I'll try to figure out maybe Azure has some Python API. Then I'll research on that. I'll find the API for that. I'll see what are the different connection things I have to use, what are authentication I have to use, define a new class on top of it, and then I'm done, right? So these are two steps. Define a new class, figure out what Azure uses, what API there is, and then transition your pipeline code to use the Azure function instead of the S3 function, right? So this is the learning, this is the curve that you have to follow to actually switch between an S3 and Azure artifact store. With ZenML, what happens is this. The pipeline code is defined in such a way that it's completely agnostic of the tool, as I said earlier. So you have this step decorator, which tells Python, so which tells ZenML that this is a machine learning step, and it has the same thing, the same code as before. So you don't have to repurpose your existing code to work with ZenML. If you have a Python, so if you have a notebook which has some code which already exists for you, you can just refactor that into these functions. So ZenML only expects you to have different functions for different steps. So for example, I have this importer step and I have this training step. And there's no mention of any uploading anywhere. Like that's strange, right? Where does the data get uploaded to the remote artifact store? So all of that happens inside the step decorator function. So ZenML knows that, okay, this data is returned as a data frame. Now, when it is returned, it goes into this step function, and then it automatically figures out what your current artifact store is, like what is the main artifact store, and it deals with the uploading logic itself. So that's automatically done. And the same is true for trainer step. So in the train step, you can see I have defined data as an input to it, but where is the data coming from? So ZenML automatically plumbs these things together. So the plumbing on the background is done by ZenML. I'll show you the actual example later on, which will be much clearer then. But just to give you an idea that the pipeline doesn't have any mention of S3 or Azure anywhere. So it's completely agnostic of what tools you're using. The only thing that you have to change here is the stack. So as I told you, the stack has the representation of all the different tools that you're using, right? And this stack needs to be updated to reflect that you have chosen a new tool right now. So what you do is this. You register, like early, what you would have done is this. You have to register an S3 artifact store. Like the flavor is S3. We use the term called flavors for different types of toolings. So artifact store is the stack component, and the flavor is the kind of tool you're going to use. So earlier you used to have an S3 artifact store. So ZenML artifact store register, pretty simple API. Flavor S3 and then the path of your bucket. So this configuration lives in the part of a stack. So you register a new stack, ZenML stack register, my stack, and then I add the artifact store here, -a this thing, and there'll be other components as well, -o orchestrator, this, that, all that. You define a new stack here, and then you can run your pipelines here. Now in the future, when you move to Azure, what you do is you just define a new component. So you can see the artifact store thing is common. So I'm defining a new artifact store, but the flavor has changed now. So from S3, it's now Azure. Now these flavors are built into ZenML. So this is the integrations I'm talking about. So if you're developing a new integration, for example, in the future you want to move to Alibaba Cloud, and if there's no integration for it, you develop an integration for that and you release it open source. So somebody else can also now use the Alibaba store. So the flavor will now be Alibaba. So that is the part of the integration part of things. So people develop integrations for ZenML and then you can keep using that. So for now, S3 and Azure already built in. The co-developers also maintain these things by themselves. But in the future, you can also have new tools there as well. So the flavor is Azure now. And again, I have to supply a path, which is my bucket container name, sorry. And then the only thing I have to do is update the stack. So ZenML stack, update my stack. And this artifact store is going to get updated. So this artifact store will be swapped out and the Azure things comes in. So that's the only change I have to do, nothing else. And then I just run my pipeline again and everything works like a charm. All right, so now I'll jump into the code, which is the real fun part. All right, so first I'll show you the architecture, like how exactly is my program organized. So this is the experiment tracking. So this is just the name of a folder which I've created. And I've just organized this in different files. You can also have it all in the same file, doesn't matter. But just for the sake of clarity and for organization, I've put this in different files. So there's a pipelines folder, there's a steps folder, and there's a run.py file. Like none of this is compulsory. Like you can have it any way you want. But this is the structure which I follow myself. So the steps here has the code for each of the steps. So as I told you earlier, you can define as add step, and then it's just a Python function. I'll show you right now. So if you go into the trainer step, is this visible? Like everybody can see this, right? Perfectly? Great. So in the trainer step, what I do is I just define a simple Python function, right? So TF trainer, a TensorFlow trainer. So it's nothing out of the ordinary. There's no ZenML here. Just a simple TF trainer step. You define the same way you do in your notebooks. It's entirely the same code. Just copy paste it here, works like charm. So you do some compilation, some fitting, all that stuff is there, and then you return the model. This thing which separates this from a normal Python function is this step decorator, which I already told you about. This step decorator is what makes ZenML know that this is a ZenML step. And then you can have multiple settings here inside this. So here you can say experiment tracker is some experiment tracker name, which is defined above. So you can see how I find the experiment tracker here. So what I do is I do client, which is the ZenML client, dot active stack. So this gives you the right now whatever stack is active for you. You can have multiple stacks at a given time. And how ZenML decides what stack to use is by taking a look at the active stack. So you can do ZenML stack set and the name of the stack, which sets it as the active stack. And then you can go ahead with the implementation. So in your code, you have this API to also know what is the active stack. So what I do is I do client.activeStack. I figure out what the experiment tracker is, and I supply that to this step. Right? So that is the idea. And I'll also take a look at the other steps, so you have some idea. Like this is not always the case like that. So for example, normalized step has no input to the step operator. Sorry, exactly. Because it doesn't require any tools to use here. It's just a simple Python function. So we are just defining it using step, nothing else. But the trainer step had an extra specification, which is the experiment tracker that it's going to use, right? So that is the idea. Now you define this steps in these ways. So you have the trainer step, you have the normalizer step, you have evaluator. Again, this is also pretty similar, simple Python functions, the way you already do it, right? So this is done. And then you have something called pipelines, right? So maybe I've not talked about pipelines before, I'll do it now. So there's a training pipeline, this is just a name, but what I'll do is, there's a step decorator here called add pipeline. So pretty similar to steps, this is how you define how the steps are linked together. So how does ZenML know, you have these multiple steps we showed you earlier, but how do these steps connect to each other? What are the inputs? How does the data flow between these different steps? All of that is part of the pipeline definition. So what I'm doing here is I'm defining a weights and biases example pipeline. This can be any name, of course, as a function. And then you have these inputs, like these are the importer, normalizer, like these are the steps in my pipeline. I take this as arguments. And then I define the linking here. So what I'm saying is this, whatever this function is, whatever the importer is, it should give me back these variables. That is the idea. I'm expecting that the importer gives me back these variables. What I'm going to do next is I'm going to link these to the different steps. So the normalizer takes the X train and Y train as the, X train and the X test as the input, and then gives out these things. So I'm just linking these values together. Like there's no implementation at all. It's completely abstract. It's just taking these different stack components and then linking the data together. Basically creating a data flow kind of diagram. So I know how data flows in this pipeline. Right, so this is definition of a pipeline. And where do you exactly initialize this pipeline? It's maybe in a separate file. You can also do it in the same file. But for the sake of clarity, I do it in a separate file, which is the run.py. So if you see here, what I do is just initializing a pipeline run. So this is the same pipeline as we defined earlier. And what I'm doing now is I'm just supplying each of the functions I defined earlier in different files as inputs to this particular function. So the pipeline takes an importer as a loader mnist. If I want to use some other importer, I can easily swap this out and then add a new importer function to it. So it doesn't have to be mnist. For example, if I want to add, say, from a custom URL, I'm very flexible to that. I don't have to change the pipeline code at all. So the linking the entire data flow diagram stays the same, but you can just swap out even the importer function. So all of the pipeline steps itself are also really composable. You can just choose between different implementations, different URLs, say test, production, all that stuff also can be handled right here entirely. So I don't have to change the pipeline code. I just supply each of the different step functions in a way I want to. And each of the step functions also takes some kind of parameters. So if I want, I can just say, if I want to change the learning rate, I don't have to change the pipeline code again. Not even the step function code again. I just have to supply different parameter to it, and then it takes care of everything else. So I'm doing initializing two runs here. The first run has, say, a learning rate of 0.003, and the other has a 0.01, just for the sake of figuring out how different it is. So this is where I initialize the runs. I have these things, and this variable, the pipeline, has multiple functions. So it has a dot run, obviously. So dot run, what it essentially does, it takes a look at the active stack again, and it figures out what the orchestrator is. And then it sends your pipeline as a Docker image to this orchestrator to run it, essentially. And that's the idea behind it. Now let's go into the running stage of things. Any doubts on how this is defined or any of the steps or how the entire pipeline is configured? No doubts? Yeah, that's great. All right, so yeah, the steps are defined, the pipeline is defined, I've initialized the pipeline, and now it's time to run. So what I'll do is this. I'll first show you what a stack looks like. So ZenML has this CLI which takes care of these things. Also, as a note here, the ZenML stack has only configurations. So it expects that you have deployed everything yourself before, right? You have deployed the cluster, you have deployed ML flow, all of that is done. You only have the values here, the connection string, the URL, all that stuff. That forms a part of the ZenML stack, essentially. But we know that people are not, at least data scientists are not that comfortable with deploying cloud applications themselves, right? So for that, we have another open source solution, which is called MLOps stacks. That's something I'm personally working on. So what that does is a series of Terraform scripts, essentially. So I'll show you that towards the end of the session, but I'm just saying that as a note. So don't worry about deployment yourself. Even that is handled through an open source solution. You can just do, say, ZenML deploy AWS minimal, and that will deploy an AWS cluster, any case cluster. It will deploy ML flow, it will set up the ingresses, the permissions, the IAM roles, all of that will be done, and ultimately it will create a stack for you. So it will create something like this for you right out of the box. So this is the ZenML stack. This is my active stack right now. So it has these different components, and each of these components have a new implementation. So I've already defined these things before. The API to do that is something similar to what I showed you earlier, ZenML artifact store register, which we showed in the slides, something like that. So all of that is handled here, and this forms a part of your stack. And right now I'm also connected to a server, which I'll show you later. So it's a common server. All of the members in my team are part of this server, and we can share the stacks as well there. All right, so ZenML stacks describe is this. Now, what I'll do is I'll do a Python run.py, simple Python application. So this run.py file, which I showed you earlier, I'm going to execute that, and we'll see how it goes. This Python file is the same as we have seen earlier. This is the same API, which is the run command. Now, ultimately, what this command will do is it takes a look at this file. It takes a look at whatever pipeline you have initialized. It then packages all of these things together. It also takes care of the integration installments. For example, if you're using S3 in it, it will make sure that all the dependencies are also installed, like Boto3 or any other kind of dependency you want. All of that will be part of the Docker image which is built right now. And it will also take care of, say, any additional dependency that you have defined in your pipelines. So all that is part of this. Yeah, definitely takes time. Not sure why. I should have recorded this previously, but okay, there's something fun in the live demos. Anyways, okay, it might take some time. I'll just show you the previous logs which I have run before. So this is how it looks like. So ultimately, it tries to build an image. It takes the base ZenML image. It takes your integration requirements. So none of that you have to do yourself. You just have to do Python run.py. And then it builds an image. It pushes it to whatever orchestrator you're using right now. So you can see it says using stack Seldon AKS to run pipeline. Now Seldon AKS is the same stack which I defined here. Like this is the Seldon AKS stack. Right? So it figures out this is the active stack, and then it tries to run your pipeline on top of that stack. Right? So it's doing the same thing now. It's building the image. This is the live version of it. It's pushing the image now. And this image will be pushed to your container registry. So this is my container registry on Azure CR. So this registry is also part of the stack here. So you can see there's a container registry component here as well. So all of the components that you need are always part of this stack. So you don't have to worry about like anything apart from this. So everything that's happening is part of this stack, essentially, right? So this is the stack. This is building the image. It has pushed the Docker image right now. So yeah, I think now we can go to the Kubeflow thing. Let me see. So right now, this stack which I'm using, if I go back to the table here, you can see the orchestrator is AKS Kubeflow, right? So this is a name which I have supplied, but the configuration here is actually the local Kubernetes context, which already has a Kubeflow cluster deployed on top of it. I'll show you how the deployment is done later on, but for now you can assume that, okay, I have these clusters, these blob storage, secret manager, all of things are deployed automatically, and I have this as part of my stack configuration, right? And now, yeah, since this is now pushed that image, you can see there's a pipeline run which has started off. So started one of pipeline run with this ID, right? So this is now running on Kubeflow, on AKS, right? So what I'll do is, I'll go into the local host. So it also takes care of port forwarding your AKS cluster's Kubeflow service to your local system. So you can just go to localhost 8080 and then it shows you all the runs there are. So if I refresh this, I think I should see the latest pipeline run here. Yeah, there it is. So there's a WannaBe pipeline. So it shows you in the first step, it has logs, all those things here. So it's running on AKS. So if you go into the pod definition, you see everything is there. You can just, this probably for debugging, there's nothing important there, but just the standard Kubeflow interface, that's all. Okay, so if I go back to this thing, okay, this is done, this is completed. But this pipeline will start running the Kubeflow pipeline, it will go on ahead and we also go to see the logs at some point. But now I can take a break and I can go to the MLOps stack. So this is the part that I was talking about deploying the applications yourself, right? So you don't have to worry about actually figuring out, say, let's start with the recipes first. So we have some things called stack recipes. So each of these recipes are responsible for creating the entire stack that you want, right? So if you take a look at the first one, it says AWS Kubeflow Kserve. This is the first recipe. And if you look at the tools installed, it says Kubeflow on EKS, S3, ECR, RDS, ML for tracking, Kserve. So these are tools that it installs by itself. So if you just do ZenML stack this recipe deploy AWS Kubeflow Kserve, it will take your AWS credentials and then create a cluster, deploy Kubeflow, create an S3 bucket, deploy all these things for yourself, and then it will give you a stack YAML file essentially, which you can directly import into ZenML. So you can do ZenML stack import and the name of the file that this creates, and then you are set essentially. So on your part, there's no extra work. You just deploy this recipe, you get a stack YAML file, you import this stack as a ZenML stack, and then you are set, essentially. You can just start running the pipelines the way I did before. You can just do python run.py, it takes then as an active stack and then goes out. So you can see there's like recipes for all the different clouds here. There's AWS, there's Azure, there's GCP. I'm actively working on this and also accepting contributions. We have a few contributions already, like there are multiple pull requests right now. So it's still a budding program, but yeah, it's exciting to actually work on this before. All right, so I'll go back to the Kubeflow pipelines. I'll refresh this and see, yeah, it's the first step is complete here. If you go into the logs, you can see the logs as well. It's pretty simple, not too standard, I think. We can keep this running and we can go to some previous things that we already seen. Like I already have this weights and biases portal open, right? So like if you go into this runs, I think there will be multiple other charts that I have. So I think this is one from a very recent run that I did. So you can see the accuracy, the loss, all that stuff is automatically tracked in the pipeline code, right? I'll just show you how that was done before. Let me go back into the trainer step. All right, so if you look at the trainer step, the only thing that is weights and biases specific is this line, the callback, essentially. So this callback is defined by the weights and biases library itself. So you can see I'm importing from weights and biases to integration.krs, and this callback is there. And this is used in this small.fit thing. So this is nothing to do with ZenML or anything else. You could still be using this if you are deploying without ZenML, right? This is the idea. Now if I want to switch to MLflow, like if I want to change the stack from weights and biases to MLflow, what I'm going to do now is this. I'll import MLflow is already there, so I don't have to import it again. And then I'll just go into this section. I'll uncomment this line, which is essentially MLflow tensor autolog. So autolog is going to take care of logging entirely all the metrics and parameters itself. That is the only thing I changed. I removed this weights and biases reference, since that's gone, and that's it. So now I have moved from weights and biases to using MLflow. Now I'm going to run the same pipeline right now, and you will see the entire application running on MLflow. That's how simple it is. So I've now changed that line. I've removed the weights and biases references. I have added an MLflow line here, right? And there's no other thing which is changed here. But I'll have to change the stack. So what I'll do now is this. I'll do a ZenML stack update. Oh, wait a second. I'll first have to see if I have an experiment tracker with ML flow already. So what I'll do is I'll do ZenML experiment tracker list. Let's see. So this will give me a list of all the experiment trackers I have registered. Okay, thank you. But in any case, if you have any questions, feel free to interrupt me. Like we can have a separate Q&A section as well. But if there's any questions, any doubts around how this works, let me know. All right, so trainer step is now completed, thankfully. So if you go into the logs here, I'm not sure if you can see, there's weights and biases logs all over the place. And you can also see there's a URL here that says where you can look at the portal. So I'll just click on this and lead me to the same page I saw earlier. It's from the latest run now. So it's where you can track all your accuracy, loss, all that stuff from the value which you did right now ran, correct? Going back to this thing, I can see I have an MLflow AKS experiment tracker as an experiment tracker already listed. So what I'm going to do now is this. To move from weights and biases to MLflow, I'll do ZenML stack update. And then Selden AKS was the name of my stack. Just remember, I'll do -e, which is like the component I'm going to update right now. And this is the name of the experiment tracker, which is the MLflow AKS experiment tracker. So this is the only command I run entirely, nothing else. So I'm just updating my stack to use the MLflow experiment tracker instead of the weights and biases experiment tracker, which is the current active experiment tracker. Right, so let's wait for this to complete. And going back, I think this is already there, it's running there. And we also have a lot of other orchestrators. Kubeflow is not the only orchestrator, like it's not just Kubeflow. You can run Azure ML, you can run Kubernetes orchestrator. If you had more time, I would have showed you multiple other orchestrators as well. And even across the clouds, it works seamlessly. So right now it's running on AKS, Kubeflow, but if I wanted to switch the stacks, the only thing which I had to do was to update the orchestrator stack component. So I'll do ZenML stack update orchestrator and then maybe a Vertex AI orchestrator or say AWS orchestrator. And then it'll run on AWS or GCP. Right, so if I go back into this thing, okay, yeah, I updated the stack. So it says it's connected to this server, it's updating the stack and then update it right now. So again, what I'll do is simply do python.py. No other changes at all. So that's how it works. Meanwhile, I'll also show you our dashboard. So it comes with an open source dashboard again. So this is the dashboard which everybody in my team uses, the ZenML dashboard. Here this is a very central place to track everything. Your all pipelines, your stack components. If you want to share your stacks with your teammates, that also you can do here, which is really helpful, by the way. If you go into the stacks here, you'll see what stacks I have created, what stacks I have shared with the team, and stacks from other people as well. That is the idea. I'll just let it load for a minute. I'll just log out. Maybe I'll use my credentials. I'm not sure if just the default will show or not. All right. So again, this is also open source. You can deploy this server on your own infrastructure, and then it can connect to different clients, and all those things can happen right through this thing. All right, so let's log in with this. For some reason, pretty slow. I'm not sure why. Yeah, let's see. All right, so it's again building the image with MLflow right now. Oh, that's good. You have a question? Oh. Yeah, so it's finished pushing. I already did run this before, so I have a cached version, thankfully. So it won't take a lot of time pushing the image. All right, let's see if the dashboard opened up. Wow. Great way to showcase the dashboard. Okay, so it's finished pushing the image. It's using this again the same stack, not another stack, the same stack, but with an updated experiment tracker component. Right? Okay. Connection timeout. I think the AWS is not working. That's cool, no problem. It tried to connect to the hosted Zen server, but it somehow failed with the connection timeout. But yeah, you get the idea. Like that's the only thing I have to change. Change the stack component, do the same python.py, and now I could have watched it on MLflow. I already have it deployed here. So you can take a look at the previous experiments I did some time back and try the same experiment, the same ideas, and the same metrics, same parameters, but tracked across different tools. So you have the same metrics here, and the weights and biases stuff also shows the same thing. The three data points for accuracy, 3 data points for loss, all that stuff is here. So across 2 different tools, very easy experimentation, very easy stack switching, all of those things is pretty simple. Stack update, that's all. So that's the idea behind it. I was hoping to show you the dashboard as well, but like, luck is not in my favor at this point. But you can check this out at app.zenml.io. So it's a live dashboard open to all. You can take a look at stacks, stack components. You can have team members. You can share your stacks with them. There's a central place to track all of your ML machine learning training, right? That is the idea behind it, essentially. That's all I have to show, I think, today. And maybe I'll go back to the slide. There are some QR codes. All right, then, thank you so much.